And
Yes.
then later on, we can upload the recording to our YouTube channels as well. So good afternoon, everyone. Thanks for joining our joint events, which is SFPE UQ Student Chapter collaboration with the Society of the Wood Science Technology, Australia Student Chapter. So we are really happy to host the event today, which we invite Professor Hirashima from the Chiba University and his PhD students, Yukito. Yukito actually exchanged to UQ Fire Group for half year. So we already know each other really well, and Yukito going to present from UQ today as well. So without further ado, both of them going to present in the topic, which is the fire resistance of massive timber elements and the fire safety design of high-resin building, high-resin timber building in Japan. Well, without further ado, the virtual stage is yours. Let's give a warm welcome to Professor Hirashima and Yukito.
Okay. Thank you, Julie. Uh, Good afternoon, everyone. Thank you for inviting me this webinar today. I'm pleased to have a chance to present our study. I'd like to thank the student from the University of Queensland. So today I'm talking about fire resistance of mass environments and fire safety design of high-rise timber buildings in Japan. Okay. First, I'd like to introduce Chiba University and our laboratory. Sorry. Chiba University is one of the national university in Japan. It has 5 campuses, and the Faculty of Engineering is located on the Nishichiba campus. The Nishichiba campus is located between Tokyo Station and Narita International Airport. It takes about just 40 minutes by local train from Tokyo Station. If you have a chance to visit Tokyo, please contact me and come to Chiba University. The Fire Safety Engineering Laboratory was established by Professor Saito in 1970. Currently, we conduct joint research with the timber structure laboratories. The laboratory has 21 members. The cooperation of graduate students is essential to carry out our research. Good. The research interests of our laboratories are structural fire safety engineering for steel, concrete, timber, and composite structures. Today, I'd like to present our study on the fire resistance of mass timber structures. Topics of the presentations are backgrounds of a study on timber structures in fire. And our studies on the mass timber elements exposed to fire, including the cooling down phase, and the current actual design of high-rise timber buildings in Japan. And the next topic is timber steel connections presented by Mr. Nakayama. So SDGs is a global issue, and timber structure contribute to SDGs because it is a renewable resource that stores carbon dioxide. Meanwhile, timber structures have a high fire risk because it is a combustible materials. In Japan, a large-scale tree plantation were carried out after World War II, but the artificial forests are now aging here. It's necessary to use it effectively to help manage forest sustainability. It's mandatory to actively use wood when constructing public buildings, and then high-rise or larger timber buildings are increasing now. So it is a complex material to handle when designing structures because of inhomogeneous and high variable due to natural materials. Also tropic and combustible material. Meanwhile, it is a lightweight and high-grade insulations comparing with another structural materials. So density and thermal conductivity of the timber is quite low values. Additionally, by using adhesive, it can be turned into mass timber elements. So the reduced cross-section method is the most popular method in the design of timber structures. It has a low thermal conductivity, so the temperature inside cross-section of mass timber element remains low during a fire, and it can be designed using standard structure calculation method. When using this method, the charring depth or charring rate of the wood must be properly determined. In Japan, the design charring depth charring depth is 0.75 millimeter per minute. This value is approximately the same as that given in Eurocode 5 for softwood. This figure shows that the result obtained by reduced cross-section method generally agreed with the fire resistance period obtained from the load-bearing fire test of the glulam beams. The reduced cross-section method can adequately evaluate the resistance of mass timber element during ISO standard fire heating. On the other hand, when considering the behavior up to the cooling down phase after fire exposure, it's inappropriate to evaluate the resistance using the reduced cross-section method. Here, I'll introduce the results of load-bearing fire test on glulam timber beams. In this experiment, we investigate not only the resistance during heating phase, but also the resistance during the cooling phase. In loading test, we also investigate the resistance when the specimen was heated for 1 hour standard fire and then left to cool naturally in the furnace for 3 hours. In the load-bearing fire test, loading was continued until the cooling phase after heating, and the failure time was investigated. In the heating tests, we investigated the change in charring depth and internal temperature after 1 hour heating. This figure shows the results of the loading test. The maximum load just after heating for 1 hour was about 30% of the maximum load at ambient temperature. Furthermore, when left to cool for further 3 hours, the maximum load decreased to about half of the maximum load just after heating for 1 hour. Looking at the photos of the beam cross-section after heating tests, the change in charring depth was small during the cooling phase. So the decrease in the resistance during the cooling down phase was due to an increase in internal temperature. The temperature at the center of the cross-section, centroid, just after heating for 1 hour was close to ambient temperature. But then the temperature rose, reaching after 100 degrees after 4 hours. In order to understand the resistance during cooling phase, it's necessary to predict the internal temperature distribution and then properly assign the mechanical property of wood according to that temperatures. Annex B of Eurocode 5 advanced calculation method gives the reduction factor for strength parallel to the grain of softened wood. The strength of wood at high temperatures decreases more in compression than in tension and significantly affected by moisture content. This has been demonstrated through previous experimental studies, and these figures are examples of those reports. So now I summarize our background. Due to the increasing social demand for the use of wood, higher or larger timber buildings are increasing, and the reduced cross-section method is reasonable for predicting the resistance of timber elements exposed to ISO fire heating. But meanwhile, the resistance of timber elements considerably decreased during the cooling down phase after the heating. We needed to understand the change in the resistance during the cooling phase, considering the strength of wood at high temperature. Next, I'd like to introduce our experimental study on influence of temperature and moisture on compressive strength of wood. We investigated the compressive behavior of softened wood at high temperature using a conventional oven and a loading device. The test parameters were temperature and heating time, and we also investigate the weight change due to water evaporation. The test specimen was loaded immediately after heating, and it took approximately 5 minutes to complete the test. This graph shows the relationship between tunnel temperature and time. And this figure shows load displacement relationships. So the temperature shown here is the set temperature of the heater, and the results are shown after heating for 2-hour heating. It can be seen that the compressive strength of the softwood decreases with increasing temperature. This figure shows the relationship between compressive strength and the internal temperature of the specimen. In this figure, the results for 100 degrees also include information on the heating time. When heated to a heater temperature of 100 degrees, the compressive strength was the lowest after 2 hours, and then recovered. The reason for this is thought to be that water remained inside after 2 hours here. When predicting the fire resistance of mass timber elements, I think that wood strength should be applied when the elements contain moisture. For this reason, the reduction ratio in Euro Code 5 is appropriate, as shown in this figure, up to 100 degrees. Next is experimental and numerical studies on load-bearing capacity of mass timber columns exposed to fire, including cooling down phase. In the load-bearing fire tests of mass timber glulam columns, the test parameters were heating time, load ratio against allowable design load for a long period, 3 pieces, and cross-sectional dimensions. After heating for the heating time, shown here, loading was continued during the cooling phase, and the failure time was investigated. These photos show the aspect of the glulam columns after the tests. When the load was large, the failure time of the column was short, resulting in crushing failure. On the other hand, when the load was small, the failure time was longer, resulting in buckling failure. This is because when heated for a long time, the column becomes slender and the bending rigidity of the radial cross-section decreases. This graph shows the relationship between furnace temperature and time for each test specimen. This photo shows the radial cross-section of a column with a square cross-section of 450 millimeter after being heated for 90 minutes and left to cool for 230 minutes. The column specimen buckled and failed 320 minutes after ignition. Buckling failure was also determined based on the amount of rotation measured of the column. Numerical analysis was also carried out on the deformation behavior of the column subject to fire heating. This figure shows a finite element analysis model. The internal temperature result from the heat transfer analysis approximately agree with the experimental temperature measured at this point shown this figure. Thermal stress analysis was conducted using stress strain curve at high temperatures with reference to the Euro-codified reduction factors. The compressive deformation obtained by FE analysis, this line data, approximately agree with the test results, regardless of the load ratio. If the mechanical properties of wood at high temperatures and the internal temperature during a fire can be properly determined, it will be possible to predict the failure time of mass timber columns. This is the numerical results of the change in compressive strength and buckling strength of columns exposed to fire heating, and also including the cooling phase. Here, PU is the compressive strength and PR is the buckling strength. The buckling strength was calculated based on the tangent modulus theory. The load-bearing capacity of the column obtained from the load-bearing fire tests were found to be between the compressive strength and the buckling strength of column exposed to higher heating, including the cooling down phase. However, it's unclear whether the condition when cooled inside the furnace the same as the condition during an actual fire. Next, I'll introduce a full-scale fire test for wooden three-story school buildings in Japan. The left photos show the exterior of the school building and the interior of the staff room, which was on fire. The right graph shows the relationship between major gas temperatures and time in the staff room. This graph shows when a flashover occurs. The room temperature quickly reached 1,000 degrees. The room temperature remained above 600 degrees even during the fire decay phase. And the red heat reaction of the timber elements continued until the frame collapsed. So the top two graphs show the temperatures in the other rooms in this test. The blue line is the 1,000 degrees. High temperature continued in other rooms as the fire decay phase. In the preliminary test, sealing material was wood. And this is other test. In the final test, the sealing material was changed to plasterboard, and the fire rod materials on the floor were also changed. This change considerably extended the time to flashover. However, the temperature during the fire decay phase remains high for a long time. So I also introduce how you can get these movies of the large-scale fire test. This test was conducted by National Institute for Land and Infrastructure Management in Japan. This is a website to get the movies. But this is in Japanese here. Also, you can get 3 fire test videos: preliminary test, preparatory test, and final test. A comparison of the 3 fire tests reviews the effect of sealing material on fire behavior. If you see the inside video, this shows the fire growth leading up to flashover. It's very exciting. So this is findings from our studies, and the next step. The strength of wood decreased considerably up to 100 degrees, and the compressive strength is highly dependent on moisture content. The changes in buckling resistance of mass columns and the failure time, including the cooling phase, can be predicted by numerical analysis. If the temperature distribution and the mechanical property at high temperatures can be appropriately determined. But from full-scale fire test of wooden 3-story school building, in case of an actual fire, room temperature is significantly different from the ISO standard of fire heating. In addition, in the case of timber structures, the room temperature remains high for a long time during the fire decay phase. A further study on the actual fire behavior of timber structures is required. So finally, I'd like to introduce actual fire safety design of high-rise timber buildings in Japan. First, brief introduction to prescriptive rules for fire safety of buildings in Japan. Fire prevention requirement varies depending on the region, use, size, and number of floors of the building. The left figure shows the required fire resistance period for load-bearing elements, which varies depending on the number of floors. Last year, the fire regulations were relaxed slightly to make it easier to use wood. These photos show the standard load-bearing fire test exposed to standard fire heating. And so in timber elements, inside load-bearing member parts, it's important, and surface temperature is confirmed, and so checked to be not tear. So fire resistant test of timber element confirmed the temperature of load-bearing member is sufficiently low and doesn't tear. This is an example for fire protection for timber element using this gypsum rod. This photo shows 11-story timber buildings. This is the most higher building in Japan of timber structures. In these buildings, the fire protection fireproof protection example is timber column, load-bearing members, and fire protection is used gypsum board, and this thickness determines the duration of fire resistance, and sacrificial layer. This is a timber finish. And you can see the timber finishing. This fireproof construction method have been confirmed to have a load-bearing capacity, including the cooling phase, and to prevent the load-bearing member from charring when subject to 2-hour ISO standard fire. The next slide shows the hybrid structure with steel elements encased by mass timber. Here. This is a fireproofing method that uses dense Japanese larch and have been proven to eliminate the red heat reaction of wood during the cooling phase after fitting of 1-hour standard fire. here. So I think the reason for stop the heat reaction of wood, one of the reason is heat transfer to the high summer content of steel members. So I'd like to summarize of these lectures. I show you understanding of fire behavior of timber structures, reduce cross-section method for the structural design, and structure fire behavior of timber element during cooling down phase, especially the load-bearing capacity of mass timber columns exposed to fire, including the cooling phase. Influence of temperature and moisture on compressive stress of wood, and actual fire behavior obtained from full-scale fire tests of timber buildings. And also introduced high-rise timber buildings with fire protection in Japan, using this span board and hybrid structure with steel elements encased by mass timbers. Okay, it's finished. Thank you for your kind attention. Thank you very much. Question? Oh, I can't hear you are clapping.
Okay.
Okay, no problem. Next presenter is Yukito, but you decide when is a question time, or
I mean, is there any quick question from audience online and or audience in this meeting room? Like, I think we could like start with Q&A. Like, if not, we can, like, maybe you need more time to think about the question. We can continue to the next one, and maybe after that we have more questions.
Just a quick question.
Yeah.
Professor Hirashima, thank you so much for this presentation.
Sorry, I please pronounce loudly. Sorry.
I think now it's good.
Professor Hirashima.
Okay, good. Thank you very much.
Thank you so much for your presentation. We learned so much from your talk. I just have one question.
Okay.
From your experience, what is the most important research question that we need to answer about that we need to answer about the fire safety of timber to be able to use it much more in our built environment?
Sorry. Most important things to construct tall timber buildings. I can't. Sorry, I can't understand your question.
Should I translate? Can you hear what he's? Can you hear what he's talking about? Or...
Preliminary. So sorry.
But he said he cannot 100% hear your question. Didn't 100% receive the question you asked.
Sorry, please,
It's in the chat.
I will just type the question in the chatting box.
Okay. Chatting box. Okay, no problem. How can I see the chatting box? Can I shut my share slide?
Yeah, sure.
Okay. Sorry. Where is okay, chat. Okay, no. Oh, sorry. I can see the chat. Thank you. It's possible. What is the most important question to be answered to be able to timber more broadly in modern buildings? Okay. So I showed one of the solution of using the timber structures. For example, fire protection by gypsum board. This is most popular method in Japan. So it's easy to improve the fire resistance of timber structure, I think. But I think so. It's also important to understand the change of resistance in timber structures during fire situation. So this is motivation of our study. Okay. Okay, thank you. And what was the justification for the changes in the building code? And do you think this is suitable for timber building given the increase for association timber structure in comparison to non-combustible structures? Okay, the justification. I think this is suitable for change because so we have to use more wood. So I agree with the change of the regulation for fire safety in Japan. So we have to understand more the fire behavior, structural fire behavior of timber structures. Okay.
Right.
Okay.
Thanks. Yeah, thanks, Professor Hirashima. I think we don't have more questions for now. So let's give the virtual stage to Yukito to present his part. And after that, we may have another Q&A session for like both of you, right? Thanks.
Okay. Thank you very much.
Can you hear my voice now?
Yeah.
Yeah. Okay. So thank you, Professor, for that great
Yes.
presentation. Hi, everyone. I'm Yukito Nakayama. I'm a PhD student at Chiba University. Right now, I'm visiting UQ as a part of my PhD research.
Okay, Chan.
Is there a okay?
Can Josh hear the room?
I think he can now. He just sent that before.
Okay.
Since Professor Hirashima just talked about the fire resistance of timber structural members, I would like to shift the focus a bit and talk about how we connect those members and how we ensure fire resistance in those connections. Excellent watching. So here's what we will be focusing on today. I will be putting a special emphasis on timber dowel connections, as they are one of the most commonly used connection types in mass timber construction. First, we will look at what dowel connections are and how they behave in a fire. Then we will explore some of the fire safety approaches used in mass timber buildings in Japan, particularly in the context of earthquakes and post-earthquake fires. Finally, we will dive into wood blocks. One of the disadvantages of this type of connection is that it has steel component inside of it. So we usually use wood plugs to conceal these steel components to reduce heat transfer, as steel has high thermal conductivity. And finally, we will discuss how they function as fire protection and their impact on the overall fire behavior of timber structures. Here's a quick look at what we will be covering today. First, I will give an overview of the topic to set the stage. Then we will dive into the fire resistance of dowel connections, followed by an explanation of fire design approaches in Japan. After that, I will walk you through the results of our two experimental programs, the heating test on dowel connections and fire tests on large-scale timber frames with dowel connections. And finally, we will wrap up the presentation with some key takeaways in the conclusion. Now let's start with a brief overview of the topic. In traditional wooden houses, carpentry connections are the go-on method. These joints are usually entirely made of timber. But in modern mass timber construction, we usually use connection that combines steel and timber. These types of connection offer several advantages like minimal cross-section reduction, high stiffness, and high load-bearing capacity. Plus, they can be prefabricated off-site, which improves construction efficiency. Broadly speaking, we have 5 main types of mass timber connection. The first connection type is a glued connection, where we use adhesive to stick two timber blocks together. This type of connections is known to behave almost like a rigid connection. We typically use this type of connection for finger joints, where we stick two laminates together. The second type is a truss plate. Truss plates have a lot of spikes that penetrate the timber to form a connection. Truss plate connections have a very high stiffness but poor ductility. We usually use this in truss joints. The third type is the through bolted connection. One of the key characteristics of this connection is that it has clearance between timber and steel, which causes initial slip in the early stage of loading. Due to its low stiffness and low bearing capacity, we usually use it as a positioning aid. The first type is a nail connection. These nails are very flexible. This type of connection has poor performance, and we usually use a lot of nails to form a stiffer connection. The last connection type is today's topic, tight fit dowel connections. The key difference from tight fit dowel connection and through bolted connection is that tight fit bolted and dowel connections have no clearance between timber and steel. And thanks to the friction between these two materials, this has a moderate stiffness and moderate load bearing capacity. And one of the key characteristics of this type of connection is that it has a high ductility. Since Professor Hirashima talked about structural members such as beams and column, I would like to put a special emphasis on dowel connection in my talk today. And here are some real-world applications of dowel connections. You can find them in many high-rise timber buildings around the world. Now that we understand the characteristics of dowel connections at ambient temperature, let's shift our focus to fire conditions. Why do they matter in structural fire engineering. In the next part of my talk, I will dive into their fire resistance and why it's crucial. Let's start by looking at pure timber members. When exposed to fire, the surface of a timber member undergoes pyrolysis, forming a char layer. Char has a very low thermal conductivity, which provides the structure with good fire insulation. However, the charring rate near connections is known to be higher than that of bare timber. As you might guess, this is because of the high thermal conductivity of steel. Given that dowel connections experience higher temperature and faster charring, how can we ensure their fire resistance? And this challenge is exactly why the fire resistance of the timber connections has become a major focus in the structural fire safety community. That being said, we can generally classify dowel connections into three main types, each with different fire performance. The first type is steel-wood-steel connections, where we sandwich a timber member with two steel plates and insert dowels through all three layers to form a connection. The second type is wood-wood-wood connections, in which we place three timber members together and embed dowels into them, creating a fully timber-based connection. The third type is steel-wood connections, where we insert slotted-in steel plate between two timber side members and secure it with dowels. Because steel has high thermal conductivity, we see that SWS connection exhibit the lowest fire performance among the three types. In contrast, WSW connections typically provide the highest fire performance, since the timber side members effectively insulate the steel plate, minimizing temperature rise in the steel. Now let's shift our focus specifically to the fire performance of unprotected wood-steel-wood connections. Many researchers have conducted fire tests on dowel connections to determine which factors most influence their fire resistance. In the next few slides, I will summarize which factors significantly affect fire performance and which ones have only a minor effect. The diagram here shows the dowel connections subjected to tension forces and shear and bending forces. One of the most critical factors is side member thickness, which correspond to the distance from the steel plate to the surface of the connection. It has been found that increasing the thickness from 75 millimeters to 100 millimeters resulted in an increase of failure time by 73%. Another important factor to consider is the clearance between members. Experiments indicated that closing the clearance led to 45% increase in a failure time, highlighting the importance of tight-fitting connections. The type of fastener also plays a role. Studies have shown that using dowels instead of bolts had a slight impact on fire performance. In a numerical parametric study, two models were compared. The one has 2 bolts and 6 dowels. The other had no bolt and 8 dowels. And increasing the number of dowels from 6 to 8 resulted in 30% increase in failure time. Additionally, increasing the lower timber's cover thickness, which corresponds to the distance from bottom dowel and the bottom surface of connection, has been found to have a modulating effect. As you might expect, adding more timber at the bottom of the connection provides extra insulation, which resulted in 20% increase in a failure time. A decreased dowel diameter also plays a role in fire performance. Studies have shown that reducing the dowel diameter from 19.2 to 12.7 resulted in 20% increase in a failure time. However, research has also indicated that simply increasing the number of dowels does not have a significant influence on fire performance. So now that we've discussed ways to reinforce the fire performance of unprotected dowel connections, let's shift our focus to fire protection method. There are 3 common approaches to protecting dowel connections in a fire. The first method is wood plugs. Wood plugs are typically embedded into dowel holes to conceal steel dowels and minimize heat transfer through steel. They work as very effective fire insulation, which slows down temperature rise within the connection. Studies have shown that even a 30 millimeter thick wood plug can increase failure time by 182%, highlighting its effectiveness as a simple yet powerful fire protection measure. Intumescent coatings are another effective fire protection method. When applying them to dowel connections, we typically cover all steel surfaces to minimize heat transfer. For steel connections, the exposed steel plates are coated with intumescent material to reduce heat flux. In wood connections, we usually fill all the gaps where the slotted end steel plate could transfer heat. Studies have shown that applying intumescent coatings to SWS connections increased failure time by 44%, while WSW connections exhibited only an 18% of increase. This suggests that intumescent coatings are more effective in SWS connections where the steel surface is more exposed. As many of us already know, plasterboards significantly extend failure time as well, offering highly effective fire protection. The findings from these studies have been applied in real-world projects, particularly in large-scale timber construction. A great example is Mjøsdana, the world's tallest pure timber building. In this building, all dowels are embedded 85 millimeters into wood. The thickness corresponds to the turning depth after 120 minutes of heating. Additionally, all connection clearances are fitted with intumescent fire strips, which expand the temperature above 150 degrees, sealing the connection against fire penetration. To validate this design, structural fire engineers conducted full-scale fire tests, providing that steel plates remained below 250 degrees even after 90 minutes of heating. Next, let's move on to the next topic. What structural engineers have done in the context of mass timber construction in Japan. As you might know, Japan is one of the most earthquake-prone countries in the world. While earthquakes are a major concern for structural engineers, they also pose serious challenges for structural fire engineers due to the risk of post-earthquake fires. For example, in the 2011 Great East Japan earthquake, 31 earthquake-induced fires were reported in Tokyo, despite being 380 kilometers away from the epicenter. Nationwide, 378 of post-earthquake fires were recorded, with key causes including ignition of debris caused by tsunami, damage of heating appliances, unexpected electrification, and gas leakage. To address these risks, we have a very strict fire regulations in Japan under its Building Standards Act. There are two fire design protocols for buildings in Japan. The first is quasi-fire resistive structure. To meet the standards, we are required to ensure that the structure does not exhibit damage that would compromise structural integrity for a specified duration of fire exposure. When we conduct a test to ensure the fire resistance of a structure, we usually use the ISO standard fire. The second protocol is fire resistive structure, which requires a building to remain intact until the fire fully burns out, even after a specified fire exposure duration of 1 to 3 hours without firefighting intervention. For this type of structure, the specimen is usually first exposed to the ISO standard fire curve for the specified duration, after which the furnace is turned off and then specimen is left unattended to assess its performance during the decay phase. To achieve quasi-fire resistance, Japan's most common design approach is the reduced cross-section method, where we assume a turning rate of 0.75 millimeters per minute, which is slightly higher than that recommended in Eurocode 5. When designing fire-resistive structures using timber, we must ensure that the surface temperature of load-bearing members does not exceed 260 degrees, which is defined as the turning temperature in the Japanese standard. In comparison, Eurocode 5 and here Australia standards typically use 300 degrees as the turning temperature, meaning that the Japanese standards is more conservative. For fire-resistive structures, we can choose between prescriptive design and performance-based design. In prescriptive design, we typically use plasterboards to keep the temperature of load-bearing members below 260 degrees, or alternatively, a steel timber hybrid system where timber serves as insulation for steel components. Performance-based design is rarely used in Japan, but involves CFD simulation or full-scale fire test. So far, we talked about fire regulations in Japan. So now let's take a look at how engineers manage to meet these requirements to design high-rise timber buildings in Japan. The first example I would like to share is the Osaka Timber Trading Hall, 3-story pure timber building. This project demonstrates how fire safety can be achieved while preserving the aesthetic and structural benefits of timber. To meet fire-resistant requirement, the building uses non-combustible mortar and sacrificial timber layers. These layers not only provide effective fire protection, but also allow the structure to maintain a natural timber appearances. The connection used in this building is WSW dowel connections. These connections are covered by mortar and timber layers, ensuring that the steel components remain insulated from heat. To verify its fire performance, a full-scale fire test was conducted. After 1 hour of fire exposure, the load-bearing member remained uncharred, as you can see on this photo, demonstrating the effectiveness of this fire protection strategy. Next, let's look at Portal Plus, Japan's tallest pure timber building, standing 11 stories high. To meet the fire regulations, all structure members are protected by plasterboards and sacrificial timber layers. The beam column connection use WWW dowel connections combined with CRI connections. These are further protected by plasterboards and timber layers, ensuring fire resistance. In a full-scale fire test, the structure was exposed to a fire for 3 hours, including the cooling phase. You can see that plasterboard remained intact, providing the effectiveness of this protection method. Finally, let's look at Japan National Stadium, a great example of hybrid steel timber construction. This stadium features steel timber hybrid trusses with a 60-meter span, combining the strength of steel with the benefit of timber. A full-scale test showed that the timber layer improved truss stiffness by 25%, while also acting as fire insulation. This demonstrates how timber can enhance both structural performance and fire safety in hybrid structures. This example demonstrates that plasterboards and sacrificial timber layers are highly effective in providing fire resistance. However, while they offer strong protection, they also come with high construction costs, which can be a major limitation for large-scale timber projects. Brilliantly, the reduced cross-section is only permitted for buildings up to 3 stories. If we want to promote timber buildings further, we need to expand the application scope of this method. However, this raises a critical question. As I explained earlier, timber around the dowel experience high temperature and faster curing. So how can we ensure the fire safety of dowel connection without relying on plasterboard? To address this question, the Japan Laminated Wood Product Association conducted a series of fire tests on timber frames with doubled connections. Their findings showed that 20mm thick wood plugs were sufficient to allow load transfer from beam to column for more than 60 minutes. Additionally, Nagaoka et al. Carried out a fire test on timber frames with doubled connections covered by 75mm thick wood plugs. Surprisingly, the specimen withstood 101 minutes of exposure to the standard fire curve, demonstrating a significantly higher fire resistance than expected. These results suggest that wood plugs serve as an effective fire protection with minimal construction effort compared to more conventional fire protection methods like plasterboard. Under these circumstances, our fire safety engineering lab at Chiba University aims to develop efficient fire design strategies for mass timber construction without relying on plasterboard. To achieve this, we have conducted 2 experimental programs: heating tests on doubled connections and full-scale fire tests on timber frame with doubled connections. In the heating test, our goal was to investigate how wood plug thickness affects temperature distribution. To study this, we prepared 6 doubled connections with wood plug thickness ranging from 10 to 60 millimeters. For the full-scale fire test, we exposed the timber frame with doubled connections to 60 minutes of standard fire, followed by a cooling phase. This test aimed to examine the fire behavior of timber frames and to understand how doubled connections influence fire performance during both heating and cooling phase. In the next two sections, I would like to share some of the findings from our two experimental programs. Let's start with heating tests. This slide shows the test specimen that we use in this heating test, which had a heating length of 4,600 millimeters, a supporting span length of 6,000 millimeters, and a beam cross-section of 600 by 360 millimeters. One key point that I want to highlight here is that the beam had 3 doubled connections, each with a different wood plug thickness ranging from 10 to 60 millimeters. We conducted the heating test with the great support of GBRC Osaka, where we heated the specimen according to the ISO standard fire curve for 120 minutes without mechanical loading. And we exposed the specimen for all sides except the top one to replicate the existence of a slab. This slide compares double head temperatures for different wood plug thicknesses. We installed thermocouples at the double heads in the top, middle, and bottom rows. And the bold lines in this graph represent the average of the 3 measured temperatures. The y-axis shows temperature and the x-axis represent times. From the graph, we can see that with 10 millimeter thick wood plugs, the temperature rose rapidly right after the test started. In contrast, with 60 millimeter thick wood plugs, the double head temperature stabilized at 100 degrees Celsius, indicating a cooling effect by moisture evaporation. This moisture-driven temperature stagnation can also be seen in the shape of char layer around the connection. With 10 millimeter thick wood blocks, the char depth around the double head was deeper than in the surrounding timber, while the 60 millimeter thick wood blocks, it was shallower. For the 10 millimeter thick wood blocks, there was less moisture ahead of the double head, so water molecules moved from high temperature zone to low temperature zone, hit the double, and evaporate quickly. Since steel conduct heat faster than timber, this led to faster char formation, creating deeper char layers around the double heads. In contrast, with 60 millimeter thick wood blocks, the higher moisture content within the thicker block requires more time for evaporation, prolonging the temperature stagnation period and delaying heat transfer, which appears to suppress char formation around the double heads. Now let's take a look at fire tests on timber frame with double connections. We tested two types of specimens, a simply supported specimen and a frame specimen with doubled connections. Both had supporting spans of 6,000 millimeters and a lowering span of 1,200 millimeters, but their structural conditions differed. In the simply supported specimen, we used pinned conditions, while in the frame specimen, we applied semi-rigid beam and restraint conditions. Additionally, we used hydraulic jacks to restrain the displacement of both ends of the extruding steel cantilevers in the frame specimen. For the frame specimen, we measured 4 forces, the applied load to the beam and the resistant forces at the ends of the steel cantilevers. So why is this? This is because we wanted to measure the bending moment distribution of the specimen. For the simply supported beam, we measured the applied load, which allows us to calculate the reaction forces at the beam end supports and determine the bending moment at the beam's midspan using structural mechanics. From the frame specimen, we measure the forward forces, the applied load to the beam, and the resistance forces at the ends of the steel cantilevers. Since we had a sufficient number of external forces measurement, we could also calculate the vertical resistance of the column. Because this specimen was statically determinate, we were able to measure the bending moment at both connection and midspan. But why is measuring bending moment so important? For the simply supported beam, the applied loads remain constant throughout the test, meaning that bending moment distribution does not change. Now, if we consider the bending capacity of the beam, it gradually decreases due to tearing and temperature rise. When the bending moment at midspan reaches the bending capacity, then bending failure occurs. However, things are different for the frame specimen. A key factor to understand here is that the ratio of the bending moment at the connection and the bending moment at beam midspan is roughly proportional to the ratio of their stiffness. So if the stiffness ratio decreases and approaches zero, then the bending moment distribution will be identical to the simply supported specimen as the bending moment at the connection becomes zero. On the other hand, if sufficiently thick wood blocks protect the double connections, preventing stiffness loss and increasing the stiffness ratio, the bending moment at the connection will increase. This phenomenon is quite beneficial. If we think about the bending moment capacity, it decreases over time due to heating and cooling. However, since the applied bending moment at the midspan redistributes to the connections, the bending moment at the midspan does not reach the bending capacity and the bending failure will be deterred. Therefore, only by measuring the bending moment distribution can we accurately describe the failure mechanism of the frame specimen. To enhance fire resistance of the connections, we applied two critical fire protection measures. First, we used glued-in wood blocks around the double heads to reduce heat transfer. Second, we kept the beam column clearance at 2 millimeters or less, minimizing the heat flux coming into the connection. Additionally, the double heads were protected with 40 millimeter wood timber blocks, ensuring both ductility and fire resistance under fire exposure. We conducted the fire test at GBRC Osaka. We preloaded the specimen to 100% of the design load, calculated using the reduced cross-section method for 60 minutes quasi-fire resistive structures. Then we exposed the specimen to the ISO standard fire for 60 minutes, turned off the furnace, and left the specimen unattended to replicate the decay phase. This slide shows the deflection time relationship of both specimens. The y-axis shows the deflection, and x-axis shows the time. The black line indicates the furnace temperature, which followed the ISO standard fire curve for up to 60 minutes and followed by cooling phase. The simply supported beam failed at 172 minutes due to bending failure, as you can see on this photo. While the frame specimen did not fail until 240 minutes. Additionally, the frame specimen exhibited lower deflection compared to simply supported beam, indicating improved fire performance under fire exposure. The left graph here shows the beam cross-section temperatures, where at 30 millimeters and 60 millimeters from the bottom, the temperature exceeded the furnace temperature during the cooling phase, indicating smoldering combustion beneath the char layer. In contrast, the right graph displays temperature trends at the double heads and centers, where the temperature stagnated or even decreased, suggesting that the wood plugs provided effective thermal insulation. So this slide shows the bending moment distribution in the frame specimen comparing 60 minutes. This slide shows the bending moment distribution in the frame specimen at 60 minutes when the heating was ended and at 240 minutes when the cooling was ended. As the beam temperature continued to rise, its stiffness and strength decreased, while the connection maintained a stable temperature, keeping their stiffness and strength unchanged. As a result, the bending moment at the midspan was redistributed to the connections. This redistribution of moment had a critical impact on the structural performance as cooling progressed. As cooling progressed, the beam's bending capacity decreased due to continuous temperature rise, and the decrease in bending capacity will be shaped like this black line. If the applied moment had exceeded the beam's bending capacity, then the structure would have failed. However, thanks to moment redistribution, the structure was able to sustain loads beyond the expected limit, effectively delaying the failure. So finally, I would like to wrap up the presentation with some key takeaways. At the beginning of the presentation, we discussed how timber smoldering timber surrounding a double faster due to high thermal conductivity of the steel dowel. We also explore the key factors influencing the fire performance of dowel connections. Our findings show that several factors play a major role in improving fire resistance. These include increasing the side member thickness, minimizing the clearance, use of dowels instead of bolts, increasing in the lower timber cover thickness, and decrease in the dowel diameter. On the other hand, the number of dowels has only minor effect on fire performance. After examining the fire performance of unprotected dowel connections, we also explored three effective fire protection methods: wood blocks, intumescent coatings, and plasterboard. Through our discussion on current fire safety engineering strategies in Japan, we found that wood blocks offer several advantages such as ease of installation and improved fire resistance. However, due to limited experimental data, we still lack a clear understanding of how wood plug thickness affects temperature distribution and how it influences the overall fire behavior of timber structures. On the other hand, plasterboards are widely used in high-rise timber buildings in Japan and provide reliable fire resistance. However, their high construction costs may limit the future growth of mass timber construction. To develop efficient fire protection strategies for mass timber construction without relying on plasterboard, we conducted 2 experimental programs, heating tests and dowel connection, and full-scale fire tests on timber frames. From these experiments, we found that moisture content may play a major role in char formation. Additionally, during the cooling phase after 60 minutes of heating, while the beam continued to lose stiffness, the connection maintained their stiffness, leading to moment redistribution. Thanks to this redistribution of bending moment from the beam to connection, bending failure of the beam was delayed. Finally, these are the references used in the presentation. For more details on the frame test, numerical simulations, and methodologies, I recommend checking the papers listed on this slide. And I will also love to connect with you on LinkedIn to continue discussion and collaborate within the global fire safety community. That concludes my presentation, and thank you for listening.
Nice photos. Thanks, Yukito. Thanks, Professor Hirashima. Is there any question from online? And is there any question from the meeting room?
I've got one, but I'm going to wait if anybody has one.
If anyone from online, you get any questions, you feel free to type your questions in the chat box or just directly unmute yourself. Right. I guess actually brave question. It's like you use Japan National Stadium as an example, or like case study show like the massive timber elements has better structure performance and the fire resistant performance. But like stadium is like a relatively unique, because it's like open space and it's a kind of the ceiling or it's pretty tall, like it's barely impacted by the fire, like not like
that's right.
It's like really different with with normal office building or apartment buildings. And I just want to know, how about like a normal office buildings to apply timber structure? Does it have benefit to the structural performance, or economically speaking, or structurally speaking? Yeah.
Right, I can see why. The reason why I keep hearing my voice from.
Oh, no, it's muted. But
Yeah, maybe don't put your headphones when you're speaking. Don't put your headphones.
Oh, yeah, that's right.
Your voice needs to reach the audience.
The reason why I wanted to introduce Japan National Stadium is that this is kind of like a good example of the performance-based fire-resistant structures, because the reason why this Japan National Stadium could use steel timber hybrid trusses as the truss system over the seat is that there is a sufficient distance between between frame and the truss joint, and they checked whether there is a sufficient distance from timber to the potential frame. So as you mentioned, this is slightly different from like actual like buildings using steel timber hybrid structures. And so if we want to use timber steel hybrid structures in like common buildings, then we will have to like increase the thickness of timber layers to further fire protect the steel members, because steel is, when the temperature of steel gets above 560 degrees, and it will lose the strength, right? So in this building, if they check that there is a sufficient distance from flame, so they just use timber as like for aesthetic reasons, and to just ensure the load bearing capacity at ambient temperatures. But if you want to apply timber steel hybrid structure in like common buildings, then we will have to increase the thickness of timber layers to insulate the steel members inside of it.
Thanks. So do you have any data, or do you have any idea when we apply the steel timber structure system to normal office building or apartment building in Japan? Is that actually it's actually more economic solution, where it's actually same, or like how's like overall speaking performance, or how that impact you?
Well, I think it is an effective way in terms of both fire protection and load bearing capacity at ambient temperatures, because as I mentioned in my presentation, timber steel hybrid structure have a higher like stiffness and load bearing capacity at ambient temperatures due to the high tensile strength of timber. And also timber works as fire insulation in case of fire. So I think steel structure with like plasterboard fire protected, and steel structure with timber protected. If you compare the fire performance and load bearing capacity at ambient temperature of those structure, then I think timber steel hybrid structure is more effective way.
Thanks. Is there any question from my audience? And is there any question from the meeting room?
Yeah. The question I have is, in the beginning of the presentation, there was a lot of interesting data on why we need to redesign those connections. For example, the use of plasterboard is expensive, or the use of metal plates, obviously acting as a heat sink. In one of those connections, you mentioned that the use of intumescent coatings, and you said that it's actually better if you have the metal connection exposed, as opposed to having it in the timber. This is something that in Australia we actually strive for the opposite, to not have from a fire point of view, they don't want to have steel exposed, or people believe that if you expose the steel and you have intumescent coating, the coating is not going to activate fast enough, and heat is going to actually be transferred to the timber. So you said there was research that has shown that they actually having exposed steel connection with intumescent being an okay design. You mentioned that on the slide.
Yeah. So your question is about, is it okay to use intumescent coatings? to protect steel
connection
like
with the timber.
components
Still the timber, because there's like a specific guidance from on it from other companies. They say we're not going to use intermessen coating steel connections because the intermessen coating is not going to activate. It's still so thin. It's going to keep losing heat, and the coating is not going to reach the critical temperature or that critical gradient that it needs to start swelling.
If you look at, sorry.
Well, I think intermessen coating is a very effective way to fire protect timber steel connections because it is easy to install, and I guess it's cost effective because I think this can be prefabricated offsite. I'm not sure about intermessen coatings so much, but I think this is a very good way to insulate steel components in timber connections. However, but we don't have like much experimental data to prove that this intermessen coating is like really effective way to protect timber connections. As far as I know, there's not much experimental data, so I cannot say for sure. But in my experience, I think wood plugs or plasterboards are better
Yes.
than intermessen coating. Yeah.
If I may, if you look at the actual, what the actual slide was saying, Yukito was saying.
Yeah, you see that it's very small increase.
It's not only about small increase. So what they've done is what he's trying to see is applying the intermessen coating on the steel on the outside is effective, or applying it on the steel inside the timber is effective. So he's not saying that one is better than the other. He's just looking at
the two, an absolute comparison rather than
it's a comparison of
between the two methods, not
where is the intermessen coating most effective? Is it applied on the steel that's exposed to the fire, or is it applied to the steel inside? Now you can, from someone who knows intermessen coating, you might for me, I find applying the intermessen coating inside maybe a bit like where the space to
it's counterproductive. Like that would be used, because there's no space for the coating to expand to implement. So, but the question was more about if you have a connect, because this is a big topic on having exposed connectors but I don't want to attend the presentation to this. It's just not that interesting.
It's no, you're not learning. It's a very nice question.
But they just applied intermessen coating to steel like components. But if you apply like transparent intermessen coating to timber side members, then I think it will increase the fire resistance so much more than this test, I think.
But I think I'm going to put justification on what you're looking there is not whether this is a better method than plasterboard, but you're comparing the location of the coating relative to each other. So it's all good.
I wonder what happens if you apply intermessen coating to the actual dowel face.
Yeah.
Like around the dowel, just around the dowels.
It might work as wood plugs.
You have wood at the back, right? So it will expand. If you put on the dowels,
Outside of the dowels, around that area. Then it will expand first on the dowels before the wood, right? Or will it expand on the wood first? The wood first, I think, right? No, the wood first. I don't know. Yeah, where will it expand first?
We need to check.
And how big is the flake? And where is located?
It's 50.
Not 50, I'm good.
It's like a strong connect with
No, because when we talk about intermessens, there's so many applications. There's a big discussion about intermessens on fire doors. There's a big discussion on intermessens in connections, for operating, for reducing flammability. There's a lot of, and all of this stuff. What was really interesting, that's not a question, it's more of an observation for me, was that very interesting in Japan, that you had a slide that you saw about fire rating requirements, and you had timber that is at the lower levels requiring higher fire rating than timber at the top, which makes sense because it's carrying the load. But this is like looking at the you're looking at very strictly from a structural point of view. If you have people that they want to evacuate in a high-rise building and they are trapped up there and they take long to evacuate, wouldn't you want to have a fire rating that is consistent throughout your timber building? Because looking at it from a structural point of view, it makes sense, but relying on higher floors having only 1 hour fire rating, then it means everyone will have to have evacuated by that, which is a reasonable time. You don't want people to stay long, but what in case someone is trapped or something? Looking at fire rating strictly from a load point of view, and not from a fire safety, it just, yeah.
That's a very good question. Actually, let's bring it from a structural point of view. Again, let's look at it from a structural point of view. If my fire rating,
Again, intervention, right? Later, you want to go to the top floor to spray some water. You don't want the stuff to be coming down on fire brigade.
yeah, if you have a fire that started on top and now you have it in the bottom, and it's been only half an hour at the bottom floor. It's already been an hour and a half and your top floor collapses. Now your lower floor has lower capacity and suddenly there is a collapse that happened upstairs. So you have an impact. Will that actually cause your entire structure to?
Yeah. Or unless the structure is designed such that it's individual failure and there's no. So that's what I thought that was a very interesting way of defining fire rating for this kind of buildings, because yeah, at what point having it makes sense from a load point of view, and that's why we design steel members sometimes or concrete reinforced concrete columns. You see them being massive at the car park level, at the basement, and then as you go up, they become thinner. But when you talk about timber, this is a little bit different because you're adding a fire safety aspect to it on top of the structural considerations, which seems to be a disconnect between the two everywhere. Yeah, very interesting.
Yeah. I think we're kind of running out of time.
Yeah.
So last minute, like really last minute question from my audience. If we receive any question from online, I think it's time to end today's webinar, and everyone can start to enjoy the weekend. And thanks to everyone to join today. Like big thanks to Hirashima and Yukito to presenting today. And yeah, and thanks everyone. Enjoy your weekend. See you till next time.
Thank you very much.
Thank you, Professor.